All right, so this is our lecture for February 11th. We're going to be looking at our worksheet from last class. There were a couple questions with our problems. So I want to remind you of our three different equations. The first was our speed. That speed was equal to distance divided by time. The second one was our force is equal to mass times acceleration. And then our last one was that acceleration is equal to our velocity divided by time. And that's what our triangles are here for. If you're looking for speed, you just covered up distance divided by time. Looking for distance, speed times time. So you can just use these equations as is. If you're wanting their traditional form, we have those. So let's go and look at question number 1. It says Fred wins the 200-meter dash in 20.3 seconds. So what is the average speed? So first of all, we know we're looking for speed. Speed should be in meters per second because it's going to be in distance over time. And we're going to look at our equations. Our first equation here, speed equals distance over time. You have a distance and you have a time, so you know that this is going to be the equation you're going to use here. So distance is going to go on top, so 200 meters on top, and then time is on bottom, so 20.3 seconds on bottom. And so essentially our problem will be 200 divided by 20.3, which that should get you 9.85, or somewhere at least close to there. I don't mind you rounding up a little bit. Just don't round up to the whole number. Kind of keep it out to the 10th at least. All right, our next problem that we're going to look at is going to be question number 3. It says Johnny accelerates at 3.2 meters per second squared. All right, this right here, it's telling you have acceleration. We know that acceleration is part of these two problems, F equals ma and A equals v over t. So let's go ahead and see what else they give us. So we have 3.2 meters per second squared for 5.1 seconds. So this is an acceleration. This is a time. After he stopped at a stop sign, how fast is he now going? Well, that means that they're looking for a speed over time or velocity, which again is a fancy word for speed. That's either in a positive or negative form. So they're looking for a velocity. We have an acceleration and a time. So that's going to be more like this last problem here. So if you're looking for acceleration, or if you are looking for your velocity, you're going to rearrange our problem here. So looking for velocity, covering up that v. Velocity should be equal to our acceleration times time. So that's why we have 3.2 times 5.1. And then that should give us our 16.32 meters per second. You got to have a calculator. You can't just pull these out of your head. So make sure that if you need help with finding a calculator online, let me know, and I can definitely send you a link to help you out. Last but not least is going to be question number 6. Jerry yells, "I love you" to Mary across the football field from one end zone to another, about 100 meters. How much later did Mary hear those words? Assume the speed of sound in air is 340 meters per second. So they're looking for a time. That's what they don't know. They know that the speed of air, or the speed at which something can travel through air, is going to be equal to 340, and the distance is 100 meters. So again, choosing the equation that has these three variables. And you would again find here this first equation. So our equation is speed equals distance over time. We're looking for time though, so we know that time is going to be distance divided by speed. So we're going to have basically 100 divided by 340, and this would get us 0.3 or 0.29. The calculator does a little something different. It doesn't just move the decimal for some reason. And I think it has something to do with the fact that you're looking at a 4 in there. And just to kind of show you, 100 divided by 340, and they're getting you this right here. So 0.29 seconds. So that's just kind of some review problems from last class, trying to show you how to work some of those math problems. And today's lecture is really going to look at Newton's three laws individually. So let's go ahead and look at this PowerPoint here. We have three laws which we look at for Newton's motion. First law is going to be that things that are in motion will stay in motion until an outside force acts upon them. That's why you have your ball right here that is moving forward until something actually moves it. It'll keep on moving otherwise. Our second law of motion is when a force acts, so pushing or pulling on an object, it can actually change the speed or the direction in which it changes. So the bigger the force, the more the object will accelerate. And last but not least is Newton's third law. That means that when a force acts on an object, there is a equal force, which will be called a reaction, that is acting in the opposite direction. Meaning that if this balloon over here is going in an upward motion, that there is an equal and opposite downward motion trying to keep it down. So let's go ahead and look at these each individually now. So looking at Newton's first law, that things will stay in motion, or that things are or will stay still until something acts upon an object. So we have an example here of Newton's first law. An object at rest will remain at rest. And then we have our interference, our outside force, where the soccer cleat is being kicked towards the soccer ball, which creates an unbalanced force. And so the object in motion will continue at that constant speed and direction until an outside force acts upon it. So again, we have our balls right over here. Our first one, there's no outside forces, the object isn't moving, and then once it's acted upon, it has unbalanced forces. It'll stay in motion until something outside of it will act upon it. So that's our Newton's third law. And so let's take a quick look at mass and inertia. So inertia we looked at is more of our kind of lift. It has an act in an opposite direction. It's almost like the saying, the heavier they are, the harder they'll fall. That's in relation to inertia. That's telling you that the faster they're moving, the more mass that's behind it, the more inertia it will produce. Inertia itself, we know we defined as the tendency of an object to resist the change in motion. So if we look at seatbelts as an example, we have a seatbelt that is going to resist the change. It'll actually prevent a person from moving forward. So giving a more detailed example here, if you're in the car and you're going down the road and the car is traveling at, let's keep it slow, about 20 miles per hour. So the car is moving at about 20 miles per hour. You're in the passenger seat. How fast are you moving? Some individuals will say, well, I'm not moving. I'm staying in the car, so I'm not actually moving. Well, the car actually is moving. Yes, you are in the car, so therefore you are also moving. So if the car is driving 20 miles an hour, you are also moving at that exact same speed. You are also moving 20 miles per hour. And so seatbelts, trying to throw in some inertia, trying to prevent you from having any further motion. If you were to get into a wreck, it'll try to resist that change. It'll try to catch you. So here's a good example. Semi-truck was carrying a big old block of concrete. Semi-truck had to stop suddenly, and the big old thing of concrete was still moving at, let's say, a pretty fast pace. And since the truck had to stop really quickly and the block wasn't held down, that block was still going 50 something miles an hour and it wasn't held back, so it continued to move forward. That's what happens when you don't have anything to hold you down. All right, let's look at Newton's second law. When a force acts, pushes, or pulls on an object, it changes the object's speed or direction. In other words, it makes an object accelerate. The bigger the force, the more the object accelerates. So, breaking this one down, you have your little girl here at the bottom. She is pushing a box, and it's going to accelerate across the floor. Here in our middle picture, she's applying the same force, but she is trying to push two boxes. So basically doubling the weight. She's only going to be able to push half as much because the weight has been doubled. If you try to add another box, well, you're tripling the weight, so she's only going to be able to move at a third of this rate, or the third of the speed at which she was initially pushing forward. Okay. So let's look at Newton's third law of motion. When a force acts on an object, there is an equal reaction that is acting in the opposite direction. This law is actually sometimes written as actions are equal and opposite. So there is always going to be an equal reaction for whatever force is being pushed forward. So here in our bottom example, you have two people. One is on the inside of the door, one's on the outside. So one's pushing, the other one's trying to pull. So I push the door pushes back on me. I pull the door pulls back on me. So that means that something is acting upon it. You will have an equal force in the opposite direction. So that's going to be our main objective today, is to go through our three laws. There is a worksheet that is posted, and then that's all we're doing today. So please make sure you do get caught up on any of your missing assignments. Your report cards are going to catch up to you pretty quickly. We've already had our interims out, so make sure that you are completing your work.